Okay, so what we're going to do now is called a titration problem. Very common in first semester chemistry, actually in all of chemistry. We do them all the time to determine the concentration of an unknown. Now in this particular problem, we're kind of reversing that. We're just looking for the number of milliliters of nitric acid that we need to drip into 41.77 milliliters of barium hydroxide. So it's a little bit of a twist on titrations, but it all works the same. So in this scenario, the nitric acid is here. We actually know the concentration of the nitric acid in the burette. It's 0.500 molar. Yeah, that's 0.500 molar. And we don't know how many milliliters of the nitric acid that we need to drip in here to reach the end point of the titration. Now let me explain the end point of the titration. Also in this Erlenmeyer flask, or representation of one, is an indicator. And the indicator changes color when we get to what we call the end point of the titration. And so the end point is just a color change. And what it's supposed to do is approximate the equivalence point of the titration, where you have stoichiometrically equivalent amounts of both acid and base. So here we go. Let's just go ahead and do the calculation. I'm actually going to show you two methods for doing it. All right, so for the first method, we're going to do straight stoichiometry. So what we're looking for is X milliliters of the nitric acid. That's what we're looking for. And so we're going to set our stoichiometry up. Here's the equal sign. What goes on the other side of the equal sign? The volume of the other stuff. And the other stuff is this 41.7 milliliters of the barium hydroxide. Okay, so we're starting out with barium hydroxide. Now, of course, we are going to convert the milliliters to liters. How do we do that? We divide by 1,000 milliliters for every 1 liter of barium hydroxide. We've got a concentration of barium hydroxide. It's 0.1603 molar. That means in every 1 liter we have 0.1603 moles of barium hydroxide. You need to remember that this is the barium hydroxide. I'm just going to put Ba here, guys, because yeah. All right, so now this is what's happened. We've canceled milliliters of the barium hydroxide, liters of the barium hydroxide. I'm now in moles of barium hydroxide. What we're going to do next is we're going to do the mole-to-mole ratio. So I go to the balanced chemical equation. The coefficient for barium hydroxide is 1. So this is 1 mole of Ba, barium hydroxide. And then the coefficient for nitric acid is 2. So that's 2 moles of H for the acid. Oh my gosh. Anyway, so that's moles of nitric acid. Now we know the concentration of nitric acid, so that's going to be 0.500 moles of nitric acid in every 1 liter of nitric acid. Last but not least, let's convert liters to milliliters. How do we do that? We multiply by 1,000 milliliters. Okay, so let's check the rest of the units. We've canceled milliliters, canceled liters for barium hydroxide. Now we've canceled moles for barium hydroxide. We're now canceling moles for the nitric acid and liters for the nitric acid, and we wind up with milliliters. Now, as far as putting this in your calculator, notice that you've got 1,000 milliliters way down here in the denominator and 1,000 milliliters up here in the numerator. I wouldn't bother putting that in my calculator because it's just going to cancel. So let's put it in the calculator. 41.77 milliliters of barium hydroxide times 1 divided by 1,000, but because I'm going to cancel the 1,000 at the end, I'm not going to put that in the calculator. So times 0.1603 molar, moles, and then times 2 divided by 1, and then divided by 0.5, and that should be all I need, which gives me 26.78 milliliters. So my answer is 26.78 milliliters. Okay. Now, this is the stoichiometric method for doing titrations. It's perfectly valid. I recommend it highly, but there is another way, which is called the equivalence method. I'm going to erase a couple of things up here just to give myself a little bit of room. So here's what the equivalence method looks like. We're going to look at the number of moles of hydrogen ion per mole of our acid, which in this case is HNO3, times the volume of, and I'm just going to put volume of the H, which is equal to the number of moles of hydroxide ion per mole of barium hydroxide. And so times the molarity of the barium hydroxide, I'm just going to put B for base, times the volume of the base. Now, let's take a look at HNO3. So here's HNO3. It's a strong acid. When it dissociates, you get 1 mole of hydrogen ion and 1 mole of nitrate, which is a spectator. We don't really care about that. This is the chemical that's doing chemistry. Now, if I have 1 mole of this, then I have 1 mole of hydrogen ion per 1 mole of HNO3. Let's take a look at the barium hydroxide because it's different. Here's the barium hydroxide. And if I dissociate the barium hydroxide, it is a strong base. I'm going to get 1 mole of barium 2+, and I'm going to get 2 moles of hydroxide ion for every 1 mole of barium hydroxide. It's like a bicycle. If I take apart a bicycle, I get 1 bicycle seat, but I get 2 wheels or 2 tires. So it's a 2-to-1 ratio. All right, so how do I use that? And by the way, this is the reason for the mole-to-mole ratio being 1-to-2 nitric acid to barium hydroxide. So here's the deal. I look at the nitric acid and I say, okay, the number of hydrogen ions per mole of nitric acid is 1. The molarity of the nitric acid is 0.500 molar. We don't know the volume of the nitric acid. That's what we want to know. And we set it equal. Now I look at the barium hydroxide. Once again, here's barium hydroxide. And every 1 mole of barium hydroxide has 2 moles of hydroxide. And remember, this is the net ionic equation for every strong acid, every strong base reaction. Okay, we're making water out of 1 hydrogen ion, I know it's sloppy, and 1 hydroxide ion. So it's a 1-to-1 ratio here. So when I'm looking at barium hydroxide, I've got 2 moles of hydroxide, that's an equal sign right there, for every 1 mole of barium hydroxide. The molarity of my barium hydroxide is 0.1603 molar, and the volume given in the problem is 41.77 milliliters of that 0.17. So 41.77 milliliters. Okay? All right. So now I just have an algebra problem to solve, and I'm solving for volume, so I'm just going to divide both sides by 1 times 0.5, and it cancels over here. I have to do the same thing over here, 1 times 0.5 molar. Now, the molarity cancels. That's not what I'm looking for. The volume in milliliters is going to stay alive. And so I have 2 times 0.1603 times 41.77 divided by 1 times 0.5. Here, in this method, I have 41.77 in the numerator, just like I do with the equivalence method. I have 0.1603 molar in the numerator, just like I do in the equivalence method. I have 2 from the mole-to-mole ratio in the numerator in the stoichiometric method, and I have 2 in the numerator of the equivalence method and 0.5 in the denominator. And so when I solve this, I get the same answer, 26.78 milliliter. It is your choice how you solve the problem. I don't care. I will tell you that the confusion is that people confuse the mole-to-mole ratio with the 2 and the 1 that you see here. The reason the 2 is here next to the barium hydroxide is because every barium hydroxide has 2 hydroxide ions. The reason I have a 1 here next to the 0.5 is because every nitric acid has only 1 mole of hydrogen ion to donate. The reason that I have a coefficient for 2 for nitric acid is because there are 2 hydroxide ions. But please don't confuse the mole-to-mole ratio with the reason for the 2 and the 1 in the equivalence method. Okay, that's all I got tonight, guys.